Hello, class. Okay, so final topic of the semester, we're going to talk about something called resonance. And we're going to look at, say we have a string that's connected to 2 points. So these two ends are fixed. And say we create a pulse on the string. Say we create a pulse like this, and it's moving to the right. And now what happens when this pulse reaches the end of the string? And if the end is like nailed down like it is here, what happens is, well, kind of two things happen. One, some energy is going to transfer to whatever is at the end of the string. If there's like another string attached to it, we'd get a wave in that string as well. Might be a different one depending on the density of the two strings. If it's attached to the wall, the energy would go into the wall. But some of the energy is directed back though. So we could have a reflected wave that looks like this. Yeah, now when the end is fixed, this reflected wave is going to be inverted with respect to the incident wave. Another way of looking at it, it's like if you have like a sine wave, a 180-degree phase shift would just flip the wave upside down. So there's a phase shift as well as it, going back to the direction. Now, if this was like a string lying on the table and this end wasn't fixed in place, this pulse would be reflected back, but it would be reflected with the same orientation it originally had. When you fix it in place, it comes back upside down. So now imagine that we create a single pulse. And it starts out moving to the right, and then it's going to reflect back, and eventually it's going to hit this starting point, and it's going to reflect off of this end, and so it's going to look like this again going to the right. Again, if this end is fixed, it's going to be inverted again, so it's back to its original orientation, and so it's going to look a lot like this wave. And if you just create one pulse, what's going to happen is it's going to keep bouncing back and forth between the two ends. Now, in the real world, that's not going to happen for very long, because energy is dissipated just in the process of a wave traveling down a string. If you had a very long rope and you just created a pulse at one end, eventually it's going to die off on its own. But, also during reflections, energy is lost from the string. It goes into, whatever it's anchored to. And so the amplitude is going to decrease every time, but you can get reflections back and forth. Okay, now imagine that we take this end of the string and we kind of give it a flick like this, create this pulse which is going to bounce back and forth, and then we do it again. So say we have two pulses now bouncing back and forth, or what if we just keep flipping this end up and down? So we just grab this end and shake it back and forth at a particular frequency. It's like each time we move this, we're creating another pulse, and they keep bouncing around in there. And remember, if we have two pulses bouncing around, when they overlap, they're going to interfere with each other. And if we just keep shaking this, we keep creating more and more pulses, and they're going to keep bouncing around. And the result is typically going to be what we call just noise. You think there's a very large number of pulses bouncing around on this string, and they're constantly interfering with each other, but they're usually doing so in a completely random way. So if you were to have this situation, we can do this in the lab, it's just this is the last topic we talk about, so there usually isn't enough time to actually do the lab and write a lab report, but it's a really cool lab where we have a string. One end is fixed to a device that moves up and down and creates these pulses, and the other end is goes over a pulley with a weight to create tension in the rope. And yeah, we can just, demonstrate this. And if you just have some random frequency, what you're going to get, if you take a picture of the string at one moment in time, it might look something like this. Just some weird, if you were to just take a picture of it, it might look something like that. And then say you take a picture at a different time, it'll be kind of the same general randomness, but a different random shape. I mean, theoretically, you could calculate what this shape would look like. You look at all the pulses that you've created and add them all up. That'd be a difficult problem to do in practice, though, because, you'd have to take into account how much energy is lost with, as it travels down the string and with each reflection. So a fairly difficult problem. But in theory, you could do this, and the result is just what we call noise. Just these random oscillations in the string. However, there are certain frequencies that will give rise to very different results. So let's say that, this is like, say, time t1, sometime t2 later. You get this pattern. Now, there's certain frequencies that you might be able to imagine how this would occur. So let's say we create this pulse that goes down and bounces back, and then on the second reflection off here, it looks just like the original wave, and it's moving in the same direction. So what if we time it so that the second wave we create is going to be, the difference between the creation of one wave and the next is the time it's going to take for this pulse to make a round trip. So again, pulse 1, it does this, comes back, and then say this is pulse 1 after, let's do this. So pulse 1 after the first reflection, and then pulse 2, or they look the same except the second one is a freshly created pulse, so it's going to have more energy and a larger amplitude. So let's say this is pulse 2 that has gone through 0 round trips. So this one went through 2 reflections. Let's say this went through a complete round trip. And so the resulting wave is going to be the sum of these two, and it's just going to be a larger amplitude wave. And again, they're going to travel together back and forth, and then when they complete that cycle, we create pulse 3, which is going to be another large amplitude wave, and it's going to keep on adding up. And so we're going to get very large amplitude oscillations. That's one property of, and again, it's just how you time the creation of these waves. If you do it at the right frequency, you can get this to happen where they always overlap. So we're oscillating it at a certain frequency. And so one property is this large amplitude, because they just keep on adding up. Now, there is a limit, of course. You can't just keep running this and get bigger and bigger waves, because it takes energy to create these oscillations. You have to grab the end and move it up and down. That takes energy, and the bigger the wave you create, the more energy is going to be lost. So due to friction and just the loss at the reflections. And so you're supplying energy at a particular rate, and if you're, initially, you're supplying enough energy where the waves just keep getting bigger and bigger, but then as they get bigger, they're losing energy more quickly, and so you'll reach a point where you're supplying energy at the same rate that energy is going to be dissipated. And so it won't continue building indefinitely. So, but we still will get much larger amplitude waves. And another thing we're going to get is what we call a standing wave pattern. It's I'll draw one example. This isn't actually the first standing wave pattern that we can get, but just something that it could look like. Where this is really one string, but this was normally the equilibrium position of the a string. And if you look at one point on the string, like let's draw a red line here. Random line. So if you look at the string driven at some random frequency, so this one here is random frequency. If you look at the amplitude, it changes. Here it's like, below this line. So the string was below the line. Now it looks like it's kind of even with it. If you look at some later time, maybe it's above the line, maybe it's below. If you just plot this point, it's going to create a picture that's random as well. It's going to look a lot like this. Its amplitude, it's going to be moving up and down, but it's going to be doing so in a very random way. Where if you look at this point, this is what we call a resonance frequency. So if we're at a resonance frequency, and this is called a standing wave pattern, even though it is moving, of course, the string is moving up and down constantly, but if you just pick one point, like this point, it's going to be oscillating up and down with a particular amplitude. And this is another really cool demonstration we can do on campus. It's unfortunate that this is the last topic we talk about in this class. So this is one string, but it's moving up and down between these two amplitudes. If you look at this point here, it has a greater amplitude of motion, but again, the point is this amplitude at any given location is consistent. And so it's really interesting. If you look at it, it kind of looks like this. It's moving very quickly, so it kind of looks like a blur, where you can see like these two regions here. But this really interesting demonstration that we can do is, we can control the frequency that we're oscillating the string. And so what we can do is we can have this, it's called a function generator, that powers this device that moves the end of the string up and down. We can have that same function generator power a strobe light, so that it's creating flashes at the same frequency. And what happens, if you were to take a picture of, if you turn off the lights in the room, so you can only see the string when it's flashing, you can actually just see the string look like this. And it appears stationary. So like in between flashes, it moves, through a complete cycle, but then when it flashes again, it's back in the same position. And so you have a string that looks like it's literally just sitting here. You cannot see it moving. And that's what it's called a standing wave pattern. So, of course, if you watch it continuously, it kind of creates a blur here, but so what's happening here is we're creating waves that bounce around, but they're timed just right. So after they complete the reflections, they create a new they interfere constructively with the next wave that is being created. And there's actually several standing wave patterns we can get by looking at, just waves on a string. I'm going to draw them. Well, not all of them. There's technically an infinite number, but in practice there's a limit. So this is the normal string. And we can get a standing wave pattern that looks like this. Or it's like the whole string just goes up and down like this. And this is the lowest frequency that will produce resonance. It creates a standing wave pattern like this. And then if you increase it, so let's say you start with a low frequency, you have noise, you turn the knob, keep increasing the frequency, eventually we're going to get something that looks like this. And again, if you hook up that strobe light, you would see a wave that just looks like this. Doesn't appear to be moving at all. And this is the lowest frequency that resonates for this string. And then if we increase the frequency, we go back to noise. And then eventually we'll get to a point where, it's like here's I think I'll just draw 4 overall. The next pattern, the next standing, right, so the next standing wave pattern is going to look like this. And I'll draw two more. So again, we increase the frequency more. And again, we get noise. And we keep increasing the frequency and we get noise. And then it starts settling into this new pattern. That looks like this. And finally, the last standing wave pattern that I'm going to draw, at least. We can keep going with this and get more and more patterns, but we can get a pattern that looks like this. So again, these are particular frequencies that result in resonance and standing wave patterns. And we want to be able to find like what frequencies will give us these resonance patterns. But first, I want to talk about a few points. Like, let's just look at this one, for instance. If you look at this point here, we have a maximum amplitude. You know, this point is oscillating up and down like this. When we have a maximum amplitude, we call this an antinode. I'll just write an A for antinode. And there's a couple points here, like the end points are always fixed. We call those nodes. And so here, you know, the end points, we're always going to have two nodes for a wave on a string. And then, you know, we'd have an antinode in the middle, in this case. Now, for the next pattern, we have the two at the ends. We have another node in the middle. And between every two nodes is an antinode. And for this pattern, we have the two at the end. And now there's two interior nodes. So basically, you can see to go from one pattern to the next, you just add another node if you want to like draw these patterns. Just add a node to the middle. So here there's no interior nodes. Here we have one interior node. Here we have two. Here we have three. So it makes drawing these patterns a lot easier. And between every pair of nodes is an antinode. Now, we're looking at, you know, these are like waves. If we look at, let's just look at this one, for instance. This distance here is a wavelength. Now, if you look at the string, it goes through one complete cycle. That's a wavelength. And then it starts repeating itself. So if you look at just like one of these from one node to the next, that's half of a wavelength. Or if you go from a node to an antinode, that's a quarter of a wavelength. So to go from one node to the next is half of a wavelength, and from one node to an antinode is a quarter. And this is kind of the key to finding the frequencies. So let me write down a few equations. We won't need it for this discussion right now, but for a wave on a string, we can find its speed if we know the tension in the string and the linear mass density, mu. And also the speed of a wave is equal to its frequency times its wavelength. So let's look at this first pattern here. From a node to a node, this whole thing here is half a wavelength. And this is the length of the string. So we can say that the length of the string is half of a wavelength. Or the wavelength is 2L, 2 times the length of the string. And if we rewrite this equation, we can say in general the frequency is the speed over the wavelength. And so if we want to write the frequency, let's see, I'm going to call this F1. I'm just trying to figure out where to write it. I'll just write it here on a small board. But so here we have V over 2L. So this is called the fundamental frequency. There's actually two names for this. It's the fundamental frequency because this is the lowest frequency that will resonate. It's also called the first harmonic. So you can use whichever you prefer. Now let's go to the next pattern. Here we can see that this is half a wavelength, that's half a wavelength. So we can say that L is equal to lambda. And I'm going to call this F2 because this is the second frequency that will resonate. So F2 is equal to V over lambda. I'm sorry. Well, V over lambda is correct, but lambda is equal to L. So F2 is V over L. Let's go to the next pattern. Here we have 3 halves, lambda equals L. So they put boxes around these, just so we can see them. So we're finding these frequencies where we get resonance. So yeah, this is 1/2 lambda, 2/2 lambda, 3/2 lambda. So 3/2 lambda equals L. Implies that lambda is 2L over 3. So F3 is V over 2L over 3. So we can write it like that. And finally, let's look at this last pattern. We have half plus 1/2. That's 1. Then 1.5, 2. So 2 lambda equals L, or lambda is L over 2. This is the fourth frequency that resonates. Boxes around these. So F4 would be V over L over 2. Okay. And what we'd like to do here is find a pattern in these frequencies. Like, if we know 1, how do we find, like, say we know 1, like, say we find this frequency. Can we find the others just based on that? And yeah, it's actually kind of easy to see. Here we have V over 2L. Let's look at the denominators. We have 2L, L. 2L, and L. And so, to get the same denominator in each case, let's multiply this one by 2 over 2. And this one, we're at 2L, we leave it. This one, we multiply by 2 over L, so we have 4 over 2L. And now we might be able to see a pattern. F1 is V over 2L. F2 is 2 times V over 2L. And F3 is 3 times V over 2L. And then we have 4 times V over 2L. In general, we can say that Fn is n times F1. So we need to know the fundamental frequency. Let's start with that. We don't really need this anymore. So F1 is V over 2L. So V is the speed of the wave. So we have like some given system in mind. Where V is the speed of the wave, and L is the length of the string. So we can find the fundamental frequency from the formula, and then just plug in whatever n value you want. That's another resonance. And so just going back to the names, this is either called the fundamental or the first harmonic. Now the harmonics are nice, saying this is the first harmonic, this is the second harmonic, this is the third, and this is the fourth. So, yeah, n is the harmonic number. Now this other notation, there's a second way you can describe these, which I don't like as much, but you've probably heard this before used in music. This is the fundamental frequency. This would be like the first overtone, and that's the second overtone. That's the third. I don't like using that overtone notation, though. If you hear like the second overtone is when n equals 3. So there's that offset of 1. So I like just calling this, I like the term fundamental frequency, but, or the first harmonic. Either one is fine, but then just second harmonic, third, and fourth. And fifth, that you can keep on going with this pattern. So waves on a string, these are the frequencies that would resonate. Okay, now, and again, applications, yeah, stringed instruments. Yeah, you have all these different strings with different densities, so they have different waves, different wave speeds, and so yeah, they resonate at different frequencies. And L can be adjusted. If you have an instrument, you can pinch the string to fix the length that it can, you get a wave between one fixed end and wherever you're holding the string at the other. So you can get it to oscillate, you can adjust the length, and you have different strings for different frequencies, or different wave speeds. And so you can create a lot of different resonance in stringed instruments. Now, one of the major types of instruments involve like sound, like air in a column type of things, like a horn or something. You can get waves to resonate in a tube, just like a tube. So I want to talk about that next. So let's say we have a speaker that's producing sound waves, and then we put a tube here. And the sound waves are, you've got like this membrane that moves in and it compresses the air. So we have a high pressure region, and that moves down the line. So we'll have like a high pressure region here. So like the membrane moves this way, compresses the air, and that high pressure region moves away. And then the membrane, so it does like this, and then it kind of moves this way. So it moves to the right, and then when it moves back, it creates a partial vacuum. So there's a low pressure region here. And then it moves to the right again and creates a high pressure region. And we get this sequence of high pressure regions with low pressure regions in between. Now, let's say we have this type of pattern, and again, these regions are moving at the speed of sound down this tube. So now we're talking about speed of sound. Just a reminder what the speed of sound is under standard conditions. Okay, now what happens when this pattern reaches the end of the tube? This end of the tube is open, so you might think, like if we compare this to the string, when the string got to the end, it just bounced back, and that's not surprising. You picture the string. The string was flat, and then when the pulse moves to the right, that's like lifting up on the string. You think like this fixed end is going to pull back down by Newton's third law. And so, it's not very surprising that we'd get a pulse coming back. But what about, here? How are we going to get a reflection when the tube is just open in this high pressure region? Let's say that just passed. So here's this high pressure region. And you think, okay, it just keeps moving, and the next one comes along, and they keep moving away. But remember, behind every high pressure region, there's a low pressure region. And so outside, we have atmospheric pressure, and this is lower than atmospheric pressure, So air from outside wants to rush into the tube now. So whenever a high pressure region passes, air wants to come in from outside so we can get a wave moving the other way as well. We can get these air rushing in, so we're kind of forcing the air this way, but then every time a high pressure region passes, we get air from the room coming back. So we can get a reflection even off the open end of a tube. And we can create resonance in a tube as well. And so that's what we want to look at next. However, there's two things we need to consider. I'm going to draw a tube like this. So in this tube, one end is open and one end is closed. Now remember, sound waves are longitudinal waves. We have this wave moving back and forth in this tube. If I look at a molecule of air, it's going to be moving back and forth because that's the direction the wave is moving, and it is a longitudinal wave. And so at the closed end, we can't have the molecules moving back and forth. So for resonance, the closed end has to be a node. Now, this is the only condition that will create resonance. And yeah, you can't have any oscillation here. Now at the open end, again, we're just looking at the conditions that will create resonance. We're going to have an antinode at the open end. Now, this is not 100% accurate. Now, you might think, well, why do we have to have an antinode at the open end? You know, we can have oscillations at the end. Why can't we have some random oscillation? Well, you can, but that's not going to produce resonance. To get resonance, we need an antinode at the open end. Now, thing is, the antinode technically does not occur exactly at the open end. It actually occurs a little bit beyond the open end. Like how far beyond depends on like the diameter of the tube, and we're not going to worry about that. We're just going to say the antinode occurs at the open end and leave it at that. And it's, not that bad of an approximation to make. So just remember, these are the conditions in which resonance will occur. Closed end is a node, and the open end has to be an antinode. So let's look at, I'm going to draw a few wave patterns, a few resonance patterns for an open tube, one that's open at both ends. So what kind of sound waves will resonate in this tube? Sorry about the noise. There. So we're going to first consider a pipe that is open at both ends. And we're going to look at 4 standing wave patterns, just like we did with the string. And the process is going to be very similar. Say we have a pipe with a length L. We're going to ignore the fact that the antinodes are a little beyond the edge of the pipe. And we'll think the fundamental frequency, that is the lowest frequency that will cause a resonance in the tube. And so if the frequency is low, the wavelength is high. So to find like the fundamental frequency, like what's the biggest wave that we can fit here, like in this tube, with an antinode on each end? And the answer is we put one node in the middle. So what this picture represents, this height above the equilibrium, or just say the height above the center, that's the amplitude of the oscillation. Now there's 2 ways you could graph these. You can look at amplitude oscillations or pressure variations. but we're going with the amplitude here. So, yeah, we put one node in the middle. This is the biggest wave that we can fit in here. And so here we have a quarter of a wavelength. And here we have another quarter. So we can, if we add them up, we can see that 1/2 lambda equals L, or lambda is 2L. And so the fundamental frequency is V over 2L. It's exactly what we got with the spring. The string. Now, what's the next biggest wave we can get? Well, we go from one node to two. So here we have a quarter going from an antinode to a node. So each of those is a quarter. And from a node to another node is half a wavelength. If we add this all up, we see lambda equals L. And so frequency here, this is F2, that would be V over L. Frequency, speed over the wavelength is L, so we have V over L. But, just like before, let's put a 2 on top and bottom, so we have the same denominator. And we can write it like this. For the second harmonic, 2 times the fundamental. So this result seems to hold up here as well, Fn. So we showed that this is true for the waves on a string. And now we're looking at waves in this pipe that's open at both ends. Seems to be holding up as well. Let's just check with the other two. So here we have 2 nodes. Let's put 3 nodes in the middle. And so here, this is a quarter. This is a quarter. Each of these is a half. So if we end up, that's a full wavelength. A quarter and a quarter is a half. So we have 3/2 lambda. So lambda is 2L over 3. And then the frequency here is V over 2L over 3, so we put the 3 on top. And we can write that as 3 times V over 2L, or 3F1. So again, it seems to be working. Let's draw one more picture and then be done with it. So we have 4 nodes now. Not the best picture, but there we go. So here we have, I'm just gonna, these are all wavelengths, but so here we have 2 full wavelengths. We start adding these 2, that's a half. So a half and a half plus a half and a half, 2 lambda equals L. So lambda is L over 2. And F4 is V over L over 2. But let's multiply the top and bottom by 2. And so again, F4 is 4 times F1. So this result seems to hold up here as well. And again, this was for a wave on a string. And now we see the exact same equations describe the frequency, the resonance frequencies of a pipe that is open at both ends. Now we have one more case to consider, and that's what we call a half-open pipe. So let's give that a go. So say we have a pipe that's open at one end and closed at the other. We can do 4 of these as well. Okay, so remember we have a node at the closed end because we're looking at amplitude. And an antinode at the open end. So like before, we want to find... Okay, so like before, we want to find the biggest wave that we can fit in here for the fundamental. So we just we go directly from the antinode to the node. And so this is a quarter of a wavelength. So lambda is equal to 4L. And so F1 is V over lambda or V over 4L. So right now we've already found something different. Here, this is for string and open pipes. Now for a closed pipe, we have V over 4L, or for a half open pipe. A half open pipe, we have a different fundamental frequency. Okay. Now let's look at the next resonance that we can get, where we put another node in the middle, and so we go like this. Not the nicest picture I've ever drawn, but let's actually fix that. Okay, so what we have here, we can write this as 2 over 4 plus 1 over 4, 3 over 4 lambda equals L, as lambda equals 4L over 3. So now the frequency here is V over 4L over 3, which is 3 times F1. So this is a bit interesting now. Before we had this relation, Fn is n times F1. Now we have to question, is that still happening? Well, the next resonance, if we call this F2, then this equation no longer holds up. So what we're going to do is we're going to say that this equation is true just by definition. So we're going to define the harmonic like the nth harmonic is the nth multiple of the fundamental frequency, and that ensures that this equation is always going to be true. You can kind of define things however you want, as long as it's logical and doesn't lead to a contradiction or something. And so in doing that, what we're going to say then is that this is the third harmonic. So for a half-open pipe, we don't have a second harmonic. It resonates at this frequency and this frequency, but nothing in between. So we just say there is no second harmonic. Now let's move on. Here we have one node in between. Let's put two nodes in, see what happens. So here we have a quarter, here's a half, and a half. Let's say 2 over 4, 2 over 4, 1 over 4, 5 over 4 lambda equals L. So lambda is 4L over 5. So the frequency here is V over 4L over 5, or 5 times F1. So we call this the fifth harmonic. And so we can kind of see the result here. Basically, for a half-open pipe, we have the fundamental frequency, and this equation is always valid because of the way we define harmonics, and so we just have to accept the fact that there are no even harmonics for a half-open pipe. And let's do one more to check, although you should probably expect by now we're going to see 7 as the next resonance. 7 times the fundamental. So we put 3 nodes in the middle. Antinode at the end. So here's a quarter, a half, half, and a half. If we add these up, we have 3 halves, or 6 over 4 plus 1 over 4, 7. I'm going to write it like this so it doesn't look like 7 over 4 lambda, or like 7 over 4 times lambda. That equals L. So lambda is 4L over 7, and then we have V over 4L over 7. So yeah, this is F7. So basically, if you want to know what frequencies are going to resonate in a tube, you need to know F1, the fundamental frequency. Or we can look at waves on a string as well, find F1. And then we have to know what type of harmonics are going to occur. So for strings or open pipes, all the integer harmonics are going to occur, or positive integers. So we have one F1, the first harmonic, second, third, and so on. For a half open pipe, we only have the odd harmonics, 1, 3, 5, and 7, and so on. And yeah, it's it for finding the resonance frequencies. And of course, this has applications in a lot of instruments. Basically, you have a column of air that's resonating. And there's actually a really interesting lab that we can do. I'll just describe it real quickly. And again, it always occurs right at the end of the semester. But if you wanted to, you could actually measure the speed of sound yourself. The only real specialized piece of equipment you need is a tuning fork. And, that's not that hard to come by, and they're not that expensive either. And then you need a tube of water that you can adjust. So let's say we have a tube that we fill with water to some extent. So we fill it up pretty high with water, and say we can raise or lower the water level. Now we skipped that chapter in the book. That's chapter 11, where we talk about how to do that, where you have like it's connected with a tube to a reservoir over here, and by raising or lowering the reservoir, you can raise or lower the water column in this tube. And so what you do is you take a tuning fork, which has a known frequency, and ring that and hold it over the tube. And well, basically, if you just hit a tuning fork, you hear a particular sound. And if you hold it over the tube, probably not much is going to happen. However, if you lower the water level, you'll find at a certain level the sound gets louder and takes on kind of a different quality. It just sounds a little different, like a clear tone. And that's because it's resonating. Yeah, if you do a good experiment, you should definitely hear the resonance. And so let's say it resonates at this level here. So this is the first level where we get a resonance. And so the water acts like a hard surface where the wave reflects off of. So we have a picture like this with the antinode and the node. And we know this is roughly a quarter of a wavelength. But remember, the antinode's actually a little bit above the end. So we can do a little bit better, and yeah, this would introduce an inaccuracy in the speed of sound. But the point is, we can measure this distance. And then if we multiply it by 4, we get the wavelength, and the speed of sound is just the frequency times the wavelength. The frequency is known because we know, it's a tuning fork. It's even written on the fork itself. You can see it. And so yeah, we can just measure this distance, but that would introduce an error because the antinode, we're not really measuring the proper distance from the node to the antinode because it occurs beyond the end of the tube a bit. So what we can do is, once we find this resonance, let's just drop the water level down some more, and until it resonates again. And so then the wave would look like this, and we can see that this distance here is half of a wavelength. So what you do is you actually mark down where the first resonance occurs, and then the second one, let's just call that L, or let's call that Y. And so Y is equal to half of a wavelength. And that's something that we can fairly easily measure. And so we know the wavelength of the sound resonating in this tube. Then we multiply it by the frequency of the tuning fork, and we know the speed of sound. So that's a way we could actually do that. A fairly straightforward way to measure the speed of sound. There's another way that's kind of interesting. You can have a horizontal tube. Now this one, tuning fork wouldn't work. You need like a more powerful speaker at one end, producing sound at a particular frequency. And what you do is you put like sawdust on the bottom of the tube, like an even layer of sawdust. And then you get this to resonate in the tube. You adjust the frequency until you get resonance. And, you know, the molecules are bouncing back and forth everywhere except a node. And so the sawdust is getting blown around everywhere except for at the nodes because the molecules aren't moving back. And so you'll find the sawdust kind of accumulating in little mounds at all the nodes. And so remember, one node to the next is half a wavelength. So you could measure the, just measure the distance between those mounds of sawdust, and that's half of a wavelength. There's another, maybe more dramatic demonstration of this. And you can see this on YouTube. But you fill this tube with propane and light it on fire. And so, well, what you do is you cut some holes in the tube. And so you fill it with propane, so there's propane coming out of these holes, and you light it on fire. So you've got these flames coming out. Yeah, there's a bunch of YouTube videos on this. One guy actually used PVC pipe. That did not seem like a good idea, but it seemed to work. And anyways, if you drive this at resonance, the pressure affects how high this column of fire is going to rise. And so again, you can actually see like an actual wave just by looking at the columns of fire. So whether you're at a node or an antinode, so when you get it to resonate, you'll actually get a pattern that might look something like this. Well, not the best picture. I can find a good YouTube video and post it. But, yeah, you can actually see the height of these columns of fire. And kind of a nice dramatic demonstration of resonance. But, yeah, I think that'll be it then for this semester. So, yeah, we'll review this tomorrow and then have the final exam.